Hello everyone. In this video we are going to talk about the design of a simple disc cam, a cam with a uniform thickness for which the follower is a knife follower, so it has a relatively sharp point. There is no roller at the end of it or anything. And we want to use the follower displacement profile, something like that, to design the shape of this cam. And then I'm gonna do it in SolidWorks for you so you see how it's done. So here, this is, for example, if you look at the engine, you know, a four-stroke engine has four parts of the cycle. So first, when the fuel and air mixture are in the chamber, the valves are closed, they are at their highest position, and the spark creates the ignition, the explosion, so we call it power. These guys go down, okay, and they still stay there. When this one comes back, now the exhaust valve opens, so the cam pushes it down, and the exhaust mixture is basically going out of the exhaust valve. Then again it comes to the intake part, and the intake valve is opened, the air comes in, the injector injects the fuel, and then again they both close, so the piston goes up and compresses them before the next ignition. So clearly you can see that in the first and the last one the valves have to stay at their highest position, and in the second one and the third one each one of the valves has to open. Okay, so there are times that the valves are just sitting there and not opening or closing, and there are times that they open and close. So the profile for displacement of these valves could be something like this, where you see there are areas that they stay there, and then there are areas that the cam will make the follower go up or down. Again, it can stay there and then it can go back to its position. These areas where the follower stays, we call it dwelling, and then we can have rise and return. Okay, and you've probably seen the shape of many of these cams, especially the ones in engine, is something like this, something kind of like an almond. So the question is, where does this shape come from? Well, because this shape depends on this profile, how this follower goes up and down, or in this case the valves, how they open and close. That will determine the shape of or the profile of the cam. So the first thing is each cam has a circle, which we call it the base circle, and so the radius of this base circle is going to be like the minimum distance between the axis of the cam and basically the tip of the follower, which, because the follower is a knife follower, so it has a sharp ending. And then as this radial distance increases, okay, as this cam rotates, the radial distance is going to increase, right? So if I draw for you here, right, let's say initially this is the point of contact, so you only have that much of a radial distance. As this guy starts to rotate, then the radial distance becomes this, then it becomes that, and you see that the radial distance is increasing, so the follower is going to rise. Then in this area you have almost an area of almost constant radius where this dwelling happens, and then it starts going down. So you see here now on the right side, now the radial distances are decreasing back to the radius of the base where you have the return. And this part here, from here to here, where the radius is almost constant, this is this initial dwelling. Okay, so you see we have rise, return, and there are two areas of no motion on the bottom and on the top. The bigger they are, the bigger rotation or bigger angular displacement it takes for the cam to make the follower move. So this is like the very basic, and there is a lot more. There are a lot of terminologies like the heel, like the lobe center line, the nose of the cam, and so on. I don't want to go into a ton of terminologies here. So this is basically how a cam and camshaft operates, like in your engine. Now, the way to go about it for a for a knife follower is, what you do is you break down this profile, this motion profile, which you can see here by this red curve. You basically break it down into a bunch of angles. Okay, so let's say if this whole thing here is 360 rotation, one full rotation, you break it down into a bunch of angles. They could be equally spaced or not equally spaced. And then at each one of these angles, right, you determine the amount of this vertical displacement. So at this angle, right, if you call it theta n or theta m or I or whatever you want to call it, at this theta I, you find how much displacement you need, and so you might call it di or ri. Let's call it ri, the radial distance, and that ri is going to be these distances that you see are radially separating. So for example, here at angle that is at 6, at angle of 6, the radial displacement is shown by f. So you see here at this angle 6, at this rotation angle 6, which is this angle, this radial displacement here is what? That is equal to f. Okay, so at these different radial lines with different angles that are determined from the x-axis, you separate these radial distances that are determined by the y-axis here, and then those endpoints you connect together and you get what? So if you connect these endpoints together, right, then you will have the profile of your cam. So this is what we are going to do in SolidWorks here. So this is my SolidWorks, this is the end result, but if I want to show you the cam alone, right? So if you want to look at the cam, this is how I did the cam. Basically, I did the exact same thing as this graph, okay? I broke it down into 18 equally distant angular displacement. So I broke the 360 into 18 of 20 degrees. So each time only 20 degrees, it is going to rotate, and I separated those radial distances. So let's take a look here. Okay, so this is what I have. This circle is for the hole, okay, for the axis of the cam. This is the base circle. This is that minimum distance, which is 22, or the distance, this radial distance is 11. So here, as you can see, I have this line, and then I created these other lines by a circular pattern, and then on them I separated the distances. So if I want to show you that here on the side, this is like my base circle, and then I created this vertical axis like this, and then I did a circular pattern for that with respect to this point, and I changed this like to 18, 20. If you want a really accurate cam, ideally you have to do it for every single degree, so you need to have 360 of these lines. But here, just we make it smaller like that. And the important thing is, since it's a pattern, if you change one of these distances, the other ones will change accordingly, and that's not what you want. So you need to go to these display relations and get rid of this pattern thing, okay? If there is a pattern, you have to find the pattern here, and you have to get rid of that pattern. So the lines are independent from each other. So now look, if I change one of them, the other ones will not change. And then, as I said, you go and separate these distances. So you say, for example, this is like 20, and then the next one is, for example, maybe another 20, right? And then this one is now increasing radially to maybe 21, and then this one goes to, for example, 23, right? And you keep going. And let me just do a few more, maybe 26. Maybe You have to make sure it's a radial distance. Maybe 28, 29, and 30. And this one might be like 31, and this one also 31. Okay, so something like this. You don't even need the other side. Okay, you do not really need the other side. Even half of it is enough because it's symmetric. Unless your cam is not symmetric, unless your motion profile, which is this one, is not symmetric. If that's not symmetric, then of course you need all of the points. But if it is symmetric, if this profile is symmetric, you just need half of that. If it's not symmetric, then you have to determine all of those distances. And then what? You need your spline command and go ahead and connect all of these endpoints together like this. And you can keep going, okay? You can connect the rest of them and create the profile. The important thing is in SolidWorks, as I mentioned, if you want to do a cam motion, you need to make sure these different splines are tangent to each other. There should be no sharp point. If there is a sharp point, the cam constraint in SolidWorks is not going to work. Okay, so that is very critical. So here, in this case, I use the, let's see. So in this case, I used a symmetric profile, as you can see, and I have applied tangency here, as you can see it, and I have applied tangency down there. Okay, otherwise it's not going to work. So that is the cam that I have. And now this is my follower. So if you look at the follower, I didn't make it a perfect sharp point. I added a little bit surface here. And the reason is if you make it a super sharp point, sometimes SolidWorks will crash. So I added a small surface here, small flat surface, very small. And the constraints that I added, I mentioned it in another video, but if you want to know it, so I have a circle here, which I made the whole of the cam concentric with it. So it only spins in place. And then I made sure that the axes of the cam and the guide here in red are concentric or coincident, the axes of them. I put them on the front plane, and I put the cam middle plane on the front plane. I applied the cam constraint between the surface of the cam and that small tip surface of the follower, as you can see. And then I added a concentricity, as I said, and a coincidence between the center of the circle and the axis of the cam, so it's right above it. And now I go to motion analysis, and here I have applied a rotary motion, a motor basically, to that edge. So the cam is going to rotate about that point. And I go to tool, I went to tools, I went to add-ins, and I made sure that SolidWorks simulation and motion analysis are both activated, as you can see. And then I came here and I used motion analysis, not basic motion. So if you do that and plot it, plot the displacement of it, which is what I did here. Okay, let me show you. So basically you go here on this XY graph and you choose the displacement category, and then you choose the linear displacement, and in this case the Y displacement, and then you choose like this surface or any surface of this small tip surface can also be used, and then you ask it to plot it for you versus time if you want, or you can have some other variable. You can have like the angle of this, but since it's constant RPM, the angle and the time, the plot is going to be very similar, except for maybe a scale. It's going to be very similar, so I can plot it versus time. And here I generate this plot, which you can see. You see here, it is going up and staying up. It's a little bit dwelling, and then it is going down, 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 a little bit dwelling here and going up and repeating itself. And you see, it's not super perfect, of course. You see, there are these variations, although it's smooth, but it's not as good as maybe you want, or maybe that's what you want. So these depend exactly on what? On those distances that I had in the cam. Right? So if I choose different distances on the cam, then the amount of dwelling and the shape of this profile would definitely change. So hopefully this video was useful to you and you learned how to create a basic cam, a disc cam for a knife follower, given the profile of what? The follower motion. How to do that theoretically and how to do it in SolidWorks and how to animate it and get the plots. And you can go back and update based on these plots that you have. So hopefully it was good and useful to you, and I will see you in my next video. Thank you.